Okay, here we have a distance time graph, and it's going to measure this little girl Tara and her journey along this path. So what we're going to be measuring is the time it takes Tara to travel along the path, and it's going to be represented on the horizontal axis. So we have time here in seconds, and we're going from 0 to 60 seconds. And also what we're going to be measuring about Tara's journey is the distance she travels along this path, and it's going to be represented on the vertical axis. So distance traveled by girl along the path. So down here, time is going to start from 0 seconds, and 0 is going to represent that exact moment when Tara steps onto the path. So what happens when she steps onto the path? She starts moving, so distance is going to be recorded vertically because she starts moving, and also time starts running as well, so time is going to be recorded horizontally. So what happens there then is on our graph that's going to look like a slope. And remember, you read your graph from left to right. So time is moving and so is her distance. So that is represented as a slope for the first 10 seconds. Then what happens is Tara's phone rings. And what it is a text from one of her friends. So she stops and she reads the text. Now she stops, which means my graph stops moving vertically for distance. But what does happen is time keeps running though. So from 10 to 15 seconds when she stood still, time keeps moving for those 5 seconds. So that looks like a horizontal line on my graph to indicate time has moved, but her distance hasn't. Then Tara puts away her phone and she decides for the next part of the journey she's going to skip. So from time 15 seconds, she's going to skip for the next 20 seconds, all the way to time 35. Okay, and she's skipping along. Okay, so time is moving horizontally, her distance is moving vertically, so that's represented as a slope. So after those 20 seconds that she was skipping, what happens? Her phone rings again. So this time she stops and stands still again for her phone call. And what happens? She's not moving, so my graph isn't moving vertically, but time still keeps rolling on. So from time 35 to 50, you can see that my graph is going to be horizontal to indicate that movement of time. Okay? And who is it on the phone? Only it's her mum making a phone call to tell her that she forgot her maths book. So what she does then, after those 15 seconds of talking to her mum, she puts her phone back in her bag and she runs back as fast as she can home. So that is for the next 10 seconds, she runs back along that path. Okay, so you can see it took her a lot less time to come back along the path on her journey home because she was in a hurry. So if you look here, what we have is we have 5 different parts to Tara's journey. So part 2 and part 4, you can see it's horizontal because time was moving on, but she wasn't moving any distance. So that's represented as a horizontal line. Okay? And then we have parts 1, 3, and 5, which are represented by a slope because they're the times that she's moving. Now, if you look at slope 3, it's a much steeper slope than slope 1. And what that indicates is that she's moving faster at part 3. Now we know this to be true because she started skipping. And then if we think about it, looking at part 5, it's actually the steepest slope of all of these slopes. And that is reasonable because that's when she ran home. So it took her a lot less time to run home, and that means she was faster on this return journey home. So what we're going to do is now we're going to look at the speed of the journey at the different sections of the graph. Okay, so in order to get the speed of the different sections here, the first thing that we're going to have to do is give a unit of measure to the distance that Tara has travelled along the path. So what we're going to do is we're going to give the unit of measure as meters along the vertical axis now. Okay, so we'll have time in seconds and distance in meters. And the next thing that we're going to need is a formula. So speed equals distance over time. Now, it's good to remember that speed is a rate of change. So what we're investigating is how is the distance changing against how the time is changing. And remember also, distance depends on time. Okay, so time is the independent variable. Time will march on regardless, and the distance here depends on that time. Okay, so let's look at part 1 and investigate what was the speed of Tara's journey as she walked along the path for part 1 of this graph. So her speed here, we can see, is distance over time, and her distance here is 5 meters. That's how much she traveled, and her time was 10 seconds. So 5 meters over 10 seconds is 0.5, and we represent the speed as meters per second. Okay, so let's look at then the speed of part 2. So in part 2, this is where she was standing still. So, you know, there's going to be absolutely no speed when she's standing still. And we can see that the numbers reflect that. So for part 2, we have time of 5 seconds, but we have no distance. So the formula is going to be distance over time, 0 over 5, which gives me 0 meters per second, which makes sense. No speed when you're standing still. Okay, let's investigate the speed of part 3 then. Now this is where she was skipping along the path. So the speed of part 3, we can see here. So what's her time going to be? So it was from time 15 to time 35. So 35 take away 15 is 20. So her time was 20, or you can see each box here represents 5 seconds. And her distance then went from 5 to 40 meters. So 40 take away 5 is 35 meters is her. 35 meters is her distance, or you can calculate that by counting the boxes. Each box represents 5 meters. So 1, 2, 3, 4, 5, 6, 7 boxes is 35 meters. So then distance over time, 35 over 20. Put that into your calculator and you get 1.75 meters per second. Okay, so that makes sense to us here because we can see that her speed is faster for when she was skipping along the graph than when she was walking along the graph, which is 0.5 meters per second. Okay, so then we look at section 4. Now remember, her mum rang her during section 4, so she was standing still for those 15 seconds. So she's going to have absolutely no speed. Okay, and the numbers tell the same story. The time equals 15 seconds, but the distance is 0. So 0 over 15 is 0 meters per second. And then finally, let's look at the speed of part 5. Now this should be fast because she was running home. Okay, so looking at this, the time that it took her to run home was 10 seconds. You can see here from 50 to 60 seconds is 10 seconds. So that's her time, 10 seconds. And then the distance she ran home was from 40 meters all the way back to 0 meters. So the distance was 40 meters, which should be 8 boxes along here. Okay, so her speed is 40 over 10, which is 4 meters per second. And that is indeed faster than 1.75 meters per second when she's just skipping, which is faster than the 0.5 meters per second when she's just walking. So she's fastest on the return journey home. Now you will notice that I have a little add-on here, and it's to talk about the fact that you'll also be used to getting the slope of a line using rise over run. Now if I was looking at this line in section 5, I would say as I read from left to right, I'm going down the stairs. So this is a negative slope. Okay, and how I would get my negative slope is I would say my run is 10. So reading from left to right, always do your run first. So I run 10 and then I do my rise or my drop. In this case, we're going down the stairs, so it's a drop. So it's a run of 10 and a drop of 40. So that's why I have this little minus here, because if you were looking at it as a slope, it would be a minus 40. Now, how that can be interpreted in terms of speed is something called velocity. Velocity is speed, but it's in a certain direction. Okay, so you see this part here. If I was looking for the velocity of Tara for part 5, it would be the minus 40 over 10, which would give me minus 4 meters per second. So you can see it's still the same speed, 4 meters per second, but what the minus tells me is the direction that she's traveling for this speed. So it's telling me she's going 4 meters per second, but she's going back on herself. She's going back home. Okay, so you can see that for the return journey, you can look at it as speed or as velocity. And I just wanted to highlight that to you because there's a huge relationship between slope and speed. And you can see that's how you can make the relationship. Okay.